welcome to the post-dinner day. Happy to introduce the last lecture of yes, but there is a few seconds and you have to start on time. So. This will be the last lecture of Zohar. Today there is also the tutorial, and Zohar is staying here for questions.
Start, or good morning. I'll start from some general comments about the famous result from many years ago by Pyrrhus, Landau, and maybe many other people who were involved. That will be important for the context of something that I'll get to a little bit later. And then I'll go back to conformal line operators in 2+1 dimensions. Maybe I'll just wait for another minute, because when people are streaming in, it's very difficult to concentrate. I see if people are still streaming in, so. 9 a.m. is an ungodly hour. Very well, so let me just remind you of some very cool story from many years ago. And you'll see that it connects very nicely to the topic of conformal line operators and their phases. So a classic result from many decades ago is that if you take a classical system on a two-dimensional lattice, no quantum mechanics, and at each point on the lattice sites, you can put either plus or minus 1. So that's the old Ising model. You put either plus 1 or minus 1 on every single lattice site, and then you write an energy functional. So the energy functional is supposed to spit out the energy of a given configuration of pluses and minuses. And well, the Ising model is saying that the energy functional is minus some j times ni and j. Okay, that's the very well-known Ising model. So you just, this notation, I'll use it a couple of times today. So when I use this notation with angled brackets, I mean that I only sum over nearest neighbor interactions. And nearest neighbors means that they're just connected by an edge. Okay, one edge, exactly. So you just take any configuration of plus minus 1, so you evaluate the energy in that fashion, and then you compute the partition function, which is a sum over all the possible configurations n. It's the sum over all the possible configurations n with the weight, which is b, beta, which is the inverse temperature, times epsilon. You get the thermodynamic partition function, and the famous question is whether the system is magnetized or not. By magnetized, what we mean is that a typical configuration under this probability distribution, the Boltzmann distribution, is where all the spins are aligned. So they're all plus 1 or minus 1 in big domains in space. I assume people heard about this notion of symmetry breaking. So one famous question is whether for some given value of beta, the Z2 symmetry, which acts on plus, sending it to minus, and minus is sent to plus, whether this Z2 symmetry is broken. Okay, that's a question of whether the system is magnetic or not. And the answer that we know is that for some high enough temperature, it's not broken. And for low enough temperatures, it is broken, and there is some phase transition. It's a completely classical model, combinatorial model. Okay? So symmetry breaking, discrete symmetry breaking in 2 classical dimensions is allowed. We learned it from the Ising model. If there are any questions, just stop me here. An interesting question that will be important for today to understand the big picture of what I'm saying today is what happens when systems are one-dimensional. So let's imagine a similar model, but on a one-dimensional classical chain. And let's assume that we have a similar energy functional. Can a one-dimensional chain be magnetized? Okay, so this is the question that was addressed by Peierls, Landau. I mean, I learned it from some Landau stuff, but probably it was developed by many people around those years. So the question is whether a one-dimensional chain can be magnetized. And the answer that is given to this question is never. So for any finite beta, there cannot be magnetic order in a classical one-dimensional system. Okay? And the argument is the following. I'm going to give you a very qualitative argument. To really prove it mathematically, I assume you have to do something much more sophisticated. So the claim is that one-dimensional chains are never magnetized, and the proof goes as follows. So a one-dimensional chain can never be magnetized because let's suppose that this was like a stable configuration where you had +1 on a big chunk of the system. It was +1, and maybe then there will be a big chain of the system which is -1, and this would be like macroscopic domains in the system. So the argument of Peierls/Landau is that this one special place where the plus turns into minus has a finite energy. And indeed, if you look at this energy functional, it will cost you exactly energy J to flip the sign of the domain. So the energy in this one site is J, but the entropy of flipping the sign is proportional to the size of the system, because this could be anywhere. This point could be anywhere in the system. So the entropy is scaling with the volume. And as you remember, at finite temperature, we don't minimize the energy. We minimize the energy minus the entropy times temperature. So therefore, at any finite temperature, however small, the entropy, which is scaling like the volume, is going to be the energy of a domain wall flipping configuration. So therefore, domain wall flipping configurations proliferate because it's entropically favorable for them to proliferate. And therefore, it's not a stable configuration to have macroscopic domains with pluses or minuses. In 2 dimensions, this argument doesn't work, because if you have a domain of pluses and a domain of minuses, they're separated by some line. And the energy scales with the perimeter of this line. And at the same time, the entropy scales like the perimeter of the line. And you have to delicately balance. The entropy and the energy kind of naively scale in the same way. And it's a very delicate balance, so symmetry breaking can happen in 2D, but not in 1 dimension. This will be important today because we will study, using the tools of conformal line operators, some classical systems with 1-dimensional chains embedded into a more complicated setup, some kind of path. And we will ask if the Peierls/Landau arguments are still correct. Okay? So I just wanted to start with this for context, for what will come soon, using much more sophisticated modern techniques. Are there any questions about this quick reminder? So now we'll get back to the problem of line operators in, extended operators or line operators in the Ising model.
Just
and
a comment. You said entropy scales with volume. I think it's log volume, right?
I'm sorry, yes, the entropy scales with the logarithm of the volume. The number of states is the exponential of the entropy, and it's the volume. So yes, the entropy scales with the logarithm of the volume. Thank you. Any other good observations?
But why is that balanced then if you have the surface against the volume?
It's not surface against the volume. It's surface against the entropy of drawing a surface. You have to ask how many ways is there to draw a domain wall. Sorry, a separator between 2 domains. So it's a domain wall. And that's an exponential of the perimeter, if you're like super naive in doing your combinatorics. And also the energy is approximately perimeter-like. So both terms are kind of similar, and you have to do a super delicate analysis to see who wins. And in fact, we know from the solution that at high temperatures, the domain will proliferate, and at low temperatures, the domain will don't proliferate. So it's a delicate balance. And in one dimension, that balance is not delicate because the energy doesn't scale with the system size, and the entropy scales with the system size logarithmically. Okay? So what I'm going to do now is that I'll have to do a lot of walking. I want to present the same problem from 3 points of view, and the last point of view will be one where the spiralist Landau argument will be questioned in somewhat more complicated scenarios. And the result is actually super surprising. So let's start from the QFT. In the QFT, we are studying the Ising model. It's a fixed point of the renormalization group, which doesn't really have a Lagrangian, but we always kind of write some kind of Lagrangian to know what we're talking about. It's a strongly coupled fixed point, but we like to write a Lagrangian so that we more or less know what we're talking about. This is a conformal field theory in 3 dimensions with Z2 symmetry, where phi goes to minus phi. And we discussed the line defect yesterday, which we called the pinning field, which was the exponent of h times phi dt. So phi at x equals to 0, t dt. And we discussed in the second lecture how to renormalize line operators and that they only have one type of divergence, etc., etc. So this line operator flows to a conformal fixed point given by h star. One thing I didn't say, but will be super important today, is that in the UV, when you define this line operator at short distances, you start from some h, which is very infinitesimal, and then h grows towards the infrared. But you have to choose a sign. Is h going to be positive or negative? Clearly, this line operator is not invariant under the Z2 symmetry. So there are actually 2 pinning fields. So there is a conformal fixed point that we call pin plus, and there is a conformal fixed point which we call pin minus, corresponding to whether h star is positive or negative. They are related by Z2 symmetry. Okay? So there are 2 conformal line operators of this type in the Ising model, corresponding to the sign of the coupling at a fixed point, because they're related by Z2 symmetry. Okay? So this is just a simple statement about the Ising model. Now, a similar thing can be done on the lattice. So if you're a fan of lattice models, there is a Hamiltonian. This is now on a 2-dimensional quantum lattice. So time is continuous, space is discrete, and we write the Hamiltonian. It's an oh, that's ferromagnetic. I think I messed up the sign. So the Hamiltonian is I'll explain what the symbols mean in a second. So this is a Hamiltonian where on each lattice site we have a qubit. So each lattice site, each site is a qubit. So the Hilbert space is a tensor product of qubits on every lattice site. And the z's and x's are just Pauli matrices acting on these qubits. And this notation again means nearest neighbor interactions. So the z's are the z Pauli matrices and the x are the x Pauli matrices. And this model can be tuned to be gapless at long distances, which is the same, and it turns out to be the same as the relativistic Ising model. So there is no defect here yet. It's a very clean translational invariant system, and people have numerically simulated it and discovered that if you tune h in units of J to be like 3.04. This flows to a gapless theory, and it's basically the same as the 3D Ising model at long distances. So it recovers Lorentz symmetry at long distances, even though it starts on the lattice. I forgot to write here one more thing. There is this entropy, the quantum entropy S. The quantum entropy of S of the pinning field defects, I wrote it yesterday, I'll write it more precisely today. It's like log of 0.6. And it's of course the same for pin minus, since they're related by symmetry. Okay, this was just the quantum entropy. And of course, it's both of them are smaller than 0 by the theorem that we discussed yesterday. Anyway, here you start from a model on the lattice of spins. At long distances, you do coarse graining, and it goes to a conformal field theory, which is Lorentz invariant. Oh, we also had a good discussion yesterday over dinner with some of you about how is it even possible that you recover Lorentz invariance from a lattice. Okay. Are there any questions about this?
That's an H perpendicular, and that's an H star, right? On the other one.
Oh, yeah, maybe it's not a good idea to use the same notation. Maybe I'll put alpha here, and alpha here, and H will be the coupling of the impurity. Okay, so now we can add to this model some deformation, which would mimic this. So we could choose a lattice site. Let's say we choose a lattice site where we put some garbage. Let's call this lattice site to be the 1, 0. Otherwise, the lattice sites are labeled by 2 integers. Let's choose this to be the 0, 0 lattice site. So we just add one more term, which is a sum over Z, which are the neighbors of 0. So we sum over this Z, this Z, this Z, and this Z, and we can think about it as an external magnetic field. So we can think about it as an external parallel magnetic field with some coefficient H, and then the long distance theory should give us the pinning field. And this clearly breaks Z2 symmetry, so let me show you that. How does the Z2 symmetry that we saw in the Ising model in the continuum act here? The Z2 symmetry is just generated by a product of all the x's over all the lattice sites. That's the Z2 generator. We just multiply all the x's in all the lattice sites. So this is a product over all the lattice sites. So this is our unit, this is our Z2 symmetry. And the first term is invariant because it has 2 z's. Remember that x and z anti-commute. So because there are 2 z's, you pick 2 minus signs. This is invariant because all the x's commute with all the x's. This is, however, not invariant because it has only one insertion of z. So it picks up a minus sign, and therefore this flows to some kind of garbage at long distances, which is z2 odd. And again, you could have chosen h to be positive or negative, so there are 2 choices here.
I'm sorry, in the last term, what is the sum?
The sum is over all the neighbors of the point where you inserted an impurity. So these are these 4 points.
So you inserted at 1, 0.
I0.
Oh, I0.
Sorry.
0 picture, okay.
But why couldn't you just insert?
I'll get to it. So this is just a lattice description of this pinning field, and this is what you should simulate if you want to test the predictions that I mentioned yesterday about the conformal dimensions, G function. And finally, there is a classical thermal 3D perspective. Here it will be much more difficult to draw because I need to draw a three-dimensional lattice somehow, which I'm completely incapable of doing. I don't know what I'm doing even. Maybe something came out of it. So you need to imagine a three-dimensional lattice. It's a classical system now, and it's an Ising type lattice. So on each lattice site you have plus minus 1 again. On each lattice site you write the same energy functional as before, and you put some coupling J, which is ferromagnetic, and I and J. And we know from simulations that this also flows to the exact same field theory on the leftmost board if you tune J to some number. So there is some J critical where where the model becomes gapless when you coarse grain, and it's the same 3D Ising model as before. And we can introduce the pinning. We can introduce some defect as follows. So now this is a Euclidean lattice. This is a line operator. So we have to choose a line, which is a chain. Okay, let's choose this chain. We choose some chain, which is embedded inside this three-dimensional lattice. And what we do on that chain is that we add the new coupling constant h, and we sum over the ni's, where I runs on some special chain, one-dimensional chain. Okay, so that's what. And here again, there is a Z2 symmetry where plus goes to minus, and clearly this is odd under that symmetry because n goes to minus n. Okay, so these are three descriptions of the. I mean, ideally, if you put it on the computer, all the three things have to agree. They have to give the same critical exponents, the same critical behavior, etc., etc.
So why is there no minus sign in front of the J's?
Yeah, this is an antiferromagnet. In the usually this will be. So this is a quantum system, and it's an antiferromagnet, while the classical systems are ferromagnets.
Okay.
But what's the difference?
There is actually no difference in this case because the lattice is bipartite, and you can just flip the sign on one half of the lattice. But in principle, so did you understand what I said about the bipartite lattice?
Not fully.
Okay, I'm saying that there is an interesting unitary that maps the ferromagnetic to the antiferromagnetic lattice, where instead of multiplying all the x's, you multiply the x's only from one sublattice. And that flips the z's on that sublattice, so that you can map ferromagnet to antiferromagnet. So it's actually the same, but it's more conventional to think about it as an antiferromagnet. Yeah.
That Hamiltonian, so three-dimensional lattice is inflator, so the choice lines doesn't matter in the Hamiltonian.
It doesn't matter, yeah, because it's translational invariant. You just choose one special line, and you add a special coupling to that line. Okay.
You can choose a line there.
Here you don't choose a line. Here you choose a point because it's a quantum system, and the line is and the defect is in the time direction.
Yeah.
Because this is a 2D system, 2 plus 1. So here it looks like an impurity. Here it looks like a line, but it's the same thing. And now come.
Right to left.
It's not obvious. This is a classical system at finite temperature.
Because like on the left-hand side, you use the time direction, which is sort of a very special direction, and on the most right-hand side, you can choose any line. That looks good.
No. Here it's. I mean, here I wrote the QFT in Euclidean signature. So maybe it's not a good notation. I can choose x0, x1. I'm just. Imagine that, let me use the notation d tau. So the Euclidean signature is 2 x's and 1 tau. The QFT is flexible enough to accommodate the physics of both of these completely different realizations. One zero temperature quantum, one finite temperature classical. But you know, why we like QFT is because it solves many problems. So QFT solves both of these completely different setups.
It's a Euclidean.
Yeah, but the QFT is flexible enough to go to Minkowski's signature and describe this physics or that physics. That's why QFT appears in many subjects in physics, because this is a statistical physics problem, that's a quantum problem, and so on. Okay, that's like more condensed matter. This is a magnetism problem in magnetism in condensed matter at low temperatures. This is a combinatorial problem of counting pluses and minuses. And the QFT appears in both. You just have to change a little bit what you mean. The same formulas.
I'm sorry, this is a very ignorant question again, but you said these are all the same in the limit of the renormalization?
Yes, long distances. And microscopically, they're super different. This is the Hilbert space of qubits with some huge matrix acting on it. This is a combinatorial system of pluses and minuses. And this is a path integral. But when you go to long distances, they all give the same thing.
And this includes the defects.
Including the defects. Yeah, so it's just, this is like an external magnetic field in an antiferromagnet. And an external magnetic field in an antiferromagnet would essentially look the same as like a chain coupled, a chain here and the same as that. So it just, all of them flow to the same thing because it's a stable infrared fixed point.
And so can I have one more?
Yeah.
So the phase diagram of the 3D easing is the same as for the easing, but it's like a water disordered phase, but more complicated.
Yeah, it's just basically the same. Basically the same, yeah.
Oh, sorry, this is another dumb question, but when you say for long distances, is this the same as letting the lattice spacing to 0?
Long distance means that you measure correlators between points which are far away,
Sure.
like many lattice spacings away from each other.
Right.
At the tuned point, you have to tune. You tune these couplings and then you start doing these measurements, and that's how you recover criticality.
And those things will become Lorentz invariant as well.
Somehow, yes. That's actually a small miracle.
But it's unrelated to letting the lattice spacing.
No, we don't take the lattice spacing to 0 because lattice spacing is given to us by the atoms in a condensed matter system. What we do is we just take correlators along many, many lattices.
I just have a minor question. Why do sum over I around 0? Why don't you just take z at 0?
I'll get to it very soon. I'm just saying this is a Z2 odd thing. If you just took that, oh, sorry, I should have said, very important. It's best for, I think, yeah, you want to remove a point from the lattice. This is like the vacancy. Some piece of garbage came there and there is some vacancy. So now there is no more X at this point, and it's best to just remove that as well. To just avoid the point 0 altogether, because we created some vacancy and then add that interaction with the vacancy. That's, I think, the cleanest way to try to simulate it. I'll get to some, and this is Z2 odd, so I'll get to some interesting modifications soon.
This is trying to clarify some misconception on my part. I always thought that when you try to go from lattice system to quantum field theory, that has something to do with the lattice spacing, it doesn't?
No, I think it's just an old way of teaching the subject, which is kind of misguided. Because the lattice spacing is given by the distance between atoms in a condensed matter system. So the long distance limit is the limit of large volume and correlation functions, which are like separated from each other by many units of the lattice spacing. But yeah, if you read like old QFT books, they take the lattice spacing to 0 together with something else, and it's not very physical somehow.
So this long distance business is what should be thought of as a quantum field.
Yeah, quantum field theory arises in the long distance limit of lattice systems. We don't take the lattice size to 0. That doesn't make sense physically. Okay. Okay, now why am I talking all about it? A great question that arose recently is, are there conformal line operators which are Z2 invariant? I constructed for you a line operator which is conformal and non-trivial at long distances, which is Z2 non-invariant. You can ask, are there invariant Z2 invariant conformal line operators in this Ising model? That's super important for simulations because some pieces of some impurities will preserve Z2. I just wrote an impurity that doesn't, but some impurities will preserve Z2. And some chains in classical systems could preserve Z2. So we're going to discuss an interesting object now, where I'm going to write a QFT line operator, which is Z2 even, which is invariant under Z2. So that's a Z2 invariant line operator in quantum field theory. This is a direct sum. So what I did, I took the fitting fields and just did a direct sum. It's a direct sum of Hilbert spaces. It's like saying that the line is a little bit degenerate. And this is now manifestly Z2 invariant. Yes.
Why couldn't you have had phi squared in the integral?
Okay, so Shai is asking why not exponents of phi squared dt. So you can analyze this, and this flows to 0 at long distances, obviously. Because phi squared starts off as dimension 1.5, right? 1.42. And this is -1, so it's highly irrelevant. Okay, so there is this construction, and the question is whether this construction is actually non-trivial, or interesting, or I'll make the question as precise as we go. So this is a line defect that is a good candidate for a conformal Z2 invariant line defect. We can calculate its entropy. So it's a direct sum. So therefore, the total entropy, the total quantum entropy of this impurity is the entropy of the first one plus the entropy of the second one. Because it's a direct sum, that's why I'm adding the sums of the exponents of the entropy. So we get exponent of log 0.6. That's the exponent, that's 0.6 plus 0.6, that's 1.2. And this is a little bit bigger than 1. This is a little bit bigger than 1. And therefore the logarithm of the quantum impurity of this direct sum is actually bigger than 0. And this could make you suspicious. It's a quantum impurity where the entropy is bigger, the log of the G function, which is the entropy, is bigger than 0. And you remember from yesterday that the trivial line defect has a quantum entropy which is exactly 0. And the renormalization group flow from this direct sum to the trivial line defect should be possible, maybe, because you can decrease the quantum entropy to 0, right? So you might suspect that maybe this line defect is unstable towards some Z2 invariant perturbations. Okay, that's the starting point. We just investigate this candidate, and we will try to understand what does it do at long distances. By itself, of course, it doesn't flow anywhere. It's just a direct sum of two conformal line operators. But there could be some deformations. So there could be some deformations in the exponent which make it flow to trivial line defect. Maybe it's fine-tuned. Well, I'll discuss it very soon. In the same vein, you could look for Z2 invariant pieces of garbage in this description, the antiferromagnet description. And I do exactly what Tin was prodding me to do already a couple of times. I'll just multiply it by Z0. And I'm good. Okay? Now this is a impurity. So here I didn't just create a vacancy. What's the physical interpretation? Before, I created a vacancy. I removed an atom from the magnet. But now I'm saying, no, I want something that's Z2 invariant. So I'm going to do something a little bit more sophisticated. I'm just going to remove the x0 component from that interaction, but I will keep the z. So essentially the defect is that I've removed the x0 interaction from one point. So it's some kind of a smaller, it's a more subtle vacancy. But this type of defect preserves Z2. So now this defect preserves Z2.
It's like changing J on something.
Yes, it's like changing J. Now this the defect preserves Z2. And actually it's a trivial thing, because you can diagonalize Z0. You see that Z0 commutes with the Hamiltonian because there is no x0 in the Hamiltonian. So Z0 commutes with the Hamiltonian, so you could say, oh, if Z0 is +1, we're back to the pinning field pin plus. If Z0 is -1, we're back to pin minus. So this obviously is the same as the direct sum. Another thing we can do here is to save this game, we can just add ni times nj, where I is on the chain, and j and I are neighbors. And that's so you do that. That essentially changes j on some line. That's all it does. It changes the effective coupling j on some line. And this again saves Z2. So it's a slightly more complicated chain. But here you get in. Yes, I'll move the board up. But here one gets into some sort of. This is where the interesting thing begins, because in this description, because Z0 commutes with the Hamiltonian, it's obvious that it's a direct sum of two Hilbert spaces. And also here it's obvious that there is a direct sum of two Hilbert spaces. Because I've just written a direct sum. But here, this is where the Peierls-Landau paradigm theorem comes into question. Because here it's not a direct sum in any obvious way. I just took a line inside the 3D classical Ising model and changed the strength of the coupling constant. So what is the infrared limit of this problem? That's the question that arose recently and drew drew a lot of attention because it's a deep question because of the following fact. Imagine that the infrared limit of this is a direct sum, so pin plus plus pin minus. If this was the answer, it would mean that a chain inside some bath could violate the Peierls-Landau argument and could be ordered. It could have two states, right? So for this reason, one has to do a renormalization group analysis of whether this is actually a stable, non-fine-tuned defect to really understand the infrared limit of this problem. Now, if you believe that the Peierls-Landau argument carries over to situations where the chain is embedded into some bigger lattice with some complicated interactions, you might be compelled to think that this is fine-tuned, and as we can preserve Z2 and destroy it completely. It turns out that it's true. So it turns out that this defect is fine-tuned, and there is an operator which has there is another operator here which has scaling dimension, we call it delta plus minus 0.85, and it's relevant. You can integrate it on the impurity, and we believe the infrared is a trivial line defect. So we try to find a Z2 invariant non-trivial line defect in the Ising model. We found a fine-tuned one, but if we add all the possible relevant operators, which are Z2 even, it turns out that it's a trivial line operator. Similarly here, you could add a Z2 invariant interaction at 0, which is just x0, with some coupling epsilon. That's completely Z2 invariant, because Z2 is generated by a product of x's. We can add it with an infinitesimal coefficient, but in the long distance limit it will grow, because we know that the scaling dimension is 0.85, and it will trivialize the line defect. Now Z0 doesn't commute with the Hamiltonian anymore, so you can flip the spin of the qubit at 0 can flip, x flips that qubit, and the dynamics is more complicated and probably flows to a trivial line defect. A trivial line defect or a trivial impurity in Ising. Okay? And finally here, if you believe all of that, this is a classical system and it's not fine-tuned in any way. So a prediction that you could make based on these arguments is that presumably this chain does not develop magnetism, and it just flows to a trivial chain. The chain becomes invisible at long distances. It's essentially a trivial line operator. And all of this seems to be true. People in the last 2 years simulated all these cases and calculated the scaling dimension of this plus-minus operator. It seems that there are no non-fine-tuned Z2 even operators in the Ising model. And in particular, this flows to a trivial line operator, and it kind of saves the Peierls-Landau argument. So that's the first thing I wanted to say about it. It seems that this line does not develop any magnetism. It doesn't flow to a direct sum of two line defects with plus-minus. So it doesn't develop magnetism, even though it's embedded in a non-trivial system. So this is comment number one. Comment number two is that people have tried to look for examples where the Peierls-Landau argument is violated. You can ask, is it more generally true that you take a classical system in 3D, you take a chain, you add some interactions, can it be that that chain is magnetized in maybe more complicated systems? Maybe not in Ising, maybe in the SO3 magnet, maybe in some more complicated magnets. And now the consensus in the literature is that the most general answer to this question is yes. The Peierls/Landau argument can be violated. Though people haven't really written a concrete example yet, but there is overwhelming evidence that in slightly more complicated classical systems like that, there will be chains which are magnetized. How does the entropy argument, how do we bypass the entropy argument? We bypass the entropy argument because the energy of a kink, now this chain is surrounded by some gapless excitations, and the energy of the kink would be logarithmically sensitive to the size of the system, just because we're surrounding the chain by some gapless system. The entropy counting is presumably the same, but the energy counting becomes more difficult because we're surrounding the system by gapless excitations. So it's a delicate balance, but I think by now the experts agree that there are examples that will violate the Peierls-Landau argument. Yeah?
So that means if the defect is embedded in a high enough dimension system, then Peierls-Landau holds it again. Because things fall off.
That's the next. I understand your idea. It could be true. I don't know. It could be a true. It could be a correct idea. I don't know. I was thinking mostly about 2 + 1. In 2 + 1 now, the consensus now, though there is no concrete paper about it, is that we will be able to violate the Peierls-Landau argument, and we will find one-dimensional chains which are ordered if they are surrounded by a gapless bulk. So if they're surrounded by a bulk that's tuned to the critical point. Though nobody wrote a concrete model yet, but I think it's by now believed to be possible. It does not work in the Ising model. So I spent the last 40 minutes explaining to you how you could have maybe achieved that in the Ising model, but because of this nasty operator that turned out to be of scaling dimension 0.85, it's relevant and it drives the system to a trivial one. It didn't work. But some preliminary computations of the scaling dimension of such operators in other models indicate that they go above 1. And so the symmetry breaking pattern becomes RG stable.
By other models, you mean like ON models?
Yes, SL3, the SL3 magnet in particular. The more physical SL3 magnet is a great candidate to look at.
Is the idea that the bigger the N, the greater the likelihood that it's
Yeah. I mean, I think that, I have some qualitative arguments that this scales linearly with N, at large N, and I think already for N = 3 it will cross 1. So actually the more physical magnet that is easier to even hook, SL3 will develop order on the chain.
Sorry, Zohar, can you give some more details on what this delta plus minus operator is?
I can do that. Yeah, I can do that, or I can. Well, I plan to do something else. I didn't plan to explain in detail what is this operator. It's the operator that destabilizes the direct sum. So the direct sum is a sum of 2 Hilbert spaces. So you can think about it as a block diagonal matrix. So this delta plus minus is the scaling dimension of an off-diagonal operator in that 2x2 matrix. So you can think about this defect as a 2x2 matrix. That's what the direct sum means. It's a one-dimensional Hilbert space plus one-dimensional Hilbert space.
It's not symmetric.
So it's an off-diagonal operator that connects the plus and the minus defects. We call it, it's called in the literature a domain wall operator because it's like, in the theory of topological defects, we have these intertwiners or defect changing operators. Probably somebody taught you about these things in this course. So this is delta plus minus. It's the scaling dimension of the defect that changes the pin plus fixed point to the pin minus fixed point. And there is a well-defined scaling dimension you can assign to it. So it's a defect changing operator or a domain wall operator. So that's the analog of the first component of Peierls' argument, which is what's the energy at the kink. But because this is surrounded by a gapless bulk, it grows logarithmically with the size of the system. And that's why you can violate the Peierls-Landau theorem in some versions of this model, but not in Ising. So people thought that maybe in Ising it will work. It doesn't, but I think in SL3 it will work. Okay. Any final questions about the Ising story of conformal line defects? Yeah.
Is this the overwhelming evidence that you mentioned earlier?
For what?
For ON or SON for n large enough, it seems like.
Yeah, so what I know is that the scaling dimension of this domain wall operator grows linearly with n at large n. So I don't know what it's going to be equal to at n = 3, of course. But at large n, it grows linearly. And if you just extrapolate, it should cross 1 by the time you're in the physical magnet O3. So it means that there is a chain inside the classical model for the O3 magnet that will polarize and will magnetize. It could be seen in an experiment even if it's true. So that's a question that's still open.
Is Z2 even because it couples with the Z delta minus plus? So them coupled together, right?
Yes.
Because it's not like immediately obvious it is Z2 even.
Yeah, it's because you can flip the picture upside down and it's the same operator. Yes. It's very similar to the off-diagonal operators you studied extensively in the BCFT of the 2D Ising, 2D free boson, or 2D Ising, I forgot. 2D Ising. Yeah, when you studied, for instance, the defect changing operator plus to minus, it's basically a higher dimensional version of the same thing. And it tells you whether this direct sum is destabilized in a non-fine-tuned situation or not.
So in the 2D, there's duality, which relates this to the ordinary boundary magnetic field flow. There's also Cramer's when you're here, right?
There is kind of, yeah.
I mean, if you fuse, so is it given, that will be given by two-dimensional defect?
It's more complicated in 2 plus 1D. Only now we can finally do some things. Okay, yeah, there was a question by Chris. Yes.
On the right-hand side of the classical case, I'm just interested why you applied Carl's that argument for the neutral line defect, but not the original case.
Yeah, in the classical model, if we just fix n on the column I to be just plus 1, that flows to the pitting field. And that's a non-trivial conformal line defect at long distances. If we do that, that's a Z2 invariant chain. And then Ni can fluctuate between plus and minus 1. And then if you believe those arguments, it should be trivial at long distances. So this should be trivial at long distances. This should be non-trivial at long distances. Because there are non-Z2 invariant line defects which are RG stable, and there are no Z2. So there are non-Z2 invariant, I don't know, you know what I want to say? There are non-Z2 invariant line defects which are RG stable, but no Z2 invariant line defects which are RG stable. Yeah, because the Landau spirals argument is about the symmetric system, and the question is whether a chain can polarize and break the symmetry spontaneously. So I have to start from a symmetric system to apply to discuss symmetry breaking. If I break Z2, there is nothing to talk about. Okay. Okay. Yes.
Is there an intuitive reason why the 2D quantum theory should be linked to the QFT?
Is there a way to say that these should be linked to the QFT? Yeah. There's no way to prove it. We just see it on the computer.
So it's like a coincidence almost, or?
Maybe coincidence is too big of a word because it happens so frequently that coincidence would be an inappropriate thing to say. It happens that many quantum antiferromagnets have critical points which are quantum filters with Lorentz invariance. But yeah, it's certainly not a coincidence, but it's also not something that I understand of why it should happen. Okay. In particular, the development of Lorentz invariance at long distances is somewhat perplexing, you could say. Yeah.
So what is the fundamental principle is minimizing the free energy or symmetry?
What is the fundamental principle?
Yes, I mean, you just talk about computation, about energy and entropy. It's going to minimize the free energy.
Yeah, we have to minimize the free energy.
Just talk about the situation matters, the violation of Pearson's Landau argument. So, which one is more fundamental?
Oh, you're asking. Well, the Pearson's Landau argument says that at no finite temperature, you can develop order on a 1D chain. It might be that when the chain is embedded into a complicated system, then the proof doesn't go through. Okay? Yeah. But it still remains to be shown and simulated, and it's just not established completely, but it's almost obviously going to work. Okay. now I'm going to switch to a new topic connecting with anomalies, because I started the course with anomalies, and I wanted to finish with showing you something along those lines. That's another open problem in another small open problem in the field, where anomalies are very important. So we will study a slightly different model now, starting from the QFT. I can also write the lattice models. I'm not sure I'll have time to do that. So it's going to be now, instead of the Ising model, we will take a complex scalar field. So now we have a complex scalar field, and we just write this interaction, and we tune to the fixed point. So that fixed point is called the O2 model. And also it's called the XY model. These are synonyms. This is some conformal field theory with O2 symmetry. O2, how does the O2 act? So the SO2 component of O2 acts by taking the complex scalar field to itself times the phase. And the other generator, which is charge conjugation, takes phi to phi star. And together they comprise the O2 group. Okay, so this is a simple fixed point that appears in lots of applications. And in particular, in the bosonic Hubbard model, it's very easy to it's very easy to write lattice models that produce this system, and it's very common. I want to describe an interesting. You can ask, what are interesting conformal line defects which preserve the full O2 symmetry? So in the Ising model, I tried to construct conformal line defects which preserve the full Z2 symmetry, and I kind of failed. We found this fine-tuned example, which could be destabilized by an operator which is completely symmetric. And you can ask, are there O2 invariant? You can ask, are there O2 invariant line defects in the O2 model? Just as a question of curiosity. And the first thing that comes to mind is to use the construction from lecture number 1. You remember that we described a quantum mechanical system with O2 symmetry in lecture number 1? Anybody can remember what it was? What was the quantum mechanical system with O2 symmetry that we spoke about? Yes, everybody. It's the particle on the ring. It was this example where flux pi. I'll choose the flux to be pi because if the flux is not pi, that quantum mechanical system has one state, and it's not an interesting impurity. It's going to be the trivial unit operator. But at flux pi, it's an interesting quantum mechanical system. And so I'm going to do the following thing. I'm going to take a new action, S, which consists of the O2 action in the upper board, in this board. So tune to the fixed point. And then I'll write the particle in a circle. I don't need to repeat it because I explained the particle in a circle. So this is going to be the action of the particle in a circle with flux pi. So it's some interesting qubit. You can think about it as a qubit. And now there is a natural way to couple the two together. And that's how we create an interesting possible interacting line defect. So we'll couple them with some new coupling constant h, which will start its life infinitesimal, 0.001, and then the renormalization group would increase it. And what we do is we take the complex scalar field phi, and we multiply it by the exponent of ix. X was the coordinate on the circle, and we took the circle to be unit radius, so x is identified with x plus 2 pi. So that's what we do, and we add the complex conjugate. That's an interesting model that we could contemplate. What happens when we take the coordinate on the circle and couple it to an O2 order parameter? This model appears in many applications recently in condensed matter, and it's called the halon. I'll explain why it's called the halon. It's from the word halo, of course. I'll explain why they call it the halon. So we'll analyze a little bit this system. It has interesting anomalies. Are there any questions about the construction?
I'm sorry, so that S particle on the circle was the previous action for the one.
Yeah, you remember that I described the quantum mechanics of a particle in a circle?
And then you're further adding this.
And I'm adding a coupling to the O2 model. Otherwise, we know what this does, we know what this does. There is 1,000 papers on this, 10,000 papers on this, but we add one more interaction.
What is that last thing, CC?
A complex conjugate.
Ah, okay.
So that the whole action is real. Yeah. Yeah.
So the defect action is on like the particle one line, which
Oh yeah. Sorry. I was extremely. I should not have done that. So this is at x equals 0 and t, and it's multiplied by a quantum mechanical variable, which is only a function of t, and we integrate it over t, and we add complex conjugate.
Do you want to use x both for space-time and...
Yes. Let me call that q. The coordinate on the circle would be q, and that would be e to the I q. Thank you.
So the line defect can be wiggly, it doesn't have to be a pure circle.
What do you mean circle? It's not a circle in space-time.
Exactly, the circle's there is in target space, right? And
No. This circle is not in target space. That's how we created qubit. No?
Yeah.
The space-time is x and t. Q is a coordinate in quantum mechanics. It's not a space-time.
Yeah, so you integrate over Q, right? In particle.
What do you mean I integrate over Q? In the path integral.
Yeah.
So the path integral is summing over all the possible functions phi of x and t, and all the possible functions q of t, where q is the location of some quantum particles of the ring, and h is some small interaction. And h, okay, so let me just talk about the symmetries. So charge conjugation used to be a symmetry where phi goes to phi star. Of course, it just takes q to negative q. That's the same charge conjugation symmetry we had in lecture number 1. And SO2, in addition to what it does on that board, also takes x to x minus q to q minus alpha. So I'm just saying this is an O2 invariant defect. And that's why it's kind of ubiquitous in some applications in condensed matter, because it preserves all the symmetries. So it appears in some interesting applications. So this is an example of a completely symmetric defect, or preserving all the symmetries. And furthermore, we know that there is some minus sign in the realization of the symmetries from lecture number 1. So there is an anomaly. So I'll just say what the anomaly implies, and then what is believed to be true about this model. You can also write a lattice system that realizes it's very simple. It's very similar to what I did here. So there is an anomaly. So if we act on the Hilbert space, if we just act on the Hilbert space instead of the space of local operators, if you just look at the local operators as I emphasized in lecture 1, there is no anomaly. It just acts like a normal O2 symmetry. But if you act on the Hilbert space, there is an anomaly. We know that C times U alpha is e to the I alpha U minus alpha C. We know that this is true. So there is an anomaly. And the anomaly is this phase. The anomaly is this phase. You can also exhibit the fact that this anomaly is a Z2 anomaly by changing variables to V alpha, which is e to the minus alpha by 2 U alpha. And then C V alpha is negative of V minus alpha C. So it's clear that this phase is really just a minus sign after a change of variables. So we know that there is an anomaly, and that has an immediate implication for the infrared limit of this interesting line defect, which is, you remember the Venn diagram? The Venn diagram of what's possible in the infrared was that it goes to the unit operator. That's unfortunately what happened in the Ising model for the Z2 invariant defects. Then there is maybe a sum of unit operators. sum of unit operators. Then there is some topological line. And then there is the most interesting case, which is conformal, the conformal defects. And so the pinning field was conformal, but when we try to make it Z2 invariant, it went all the way to the most trivial case. But the anomaly here has an implication, which is that the halon is certainly not the unit operator at long distances. Why? It's essentially because of the anomaly. If the defect was completely trivial, let's say H flowed to 0 at long distances for some reason, it would still not be a unit operator because there is a twofold degeneracy in the Hilbert space. And so it would at the very least be 1 plus 1. So even if the qubit completely decoupled from the bulk, it will be 1 plus 1. Furthermore, if the qubit doesn't decouple from the bulk and it flows to some strong coupling thing, it cannot be trivial. It just cannot be trivialized because of the anomaly. Is that clear?
Sorry, could I back up a little bit? So H here is the quantization of this whole system here, like this halon system that you wrote down?
The Hilbert space?
Yeah.
Yes.
And
it's the whole system. It's the defect tensor. This is not a direct sum. It's defect tensor bulk. Because the whole Hilbert space is the tensor product of the defect Hilbert space and the bulk.
I see. And then the symmetries are just acting as tensor product.
The symmetries act as a tensor product, but because of the defect, there is a minus sign.
Yeah. Right. So and this relation is coming from the earlier.
And this minus sign is what I spent the first lecture, last half an hour on.
So, there is no anomaly coming from the O2 model that.
That's right. That's right. So if there was also an anomaly in the O2 model, it would be much more complicated. And I don't even know if the literature, the SIM-TFT literature, developed the technology of understanding how anomalies in the bulk and anomalies on defects talk to each other. I don't even know if in the categorical world this was developed. Here it's quite simple because there is no anomaly in the bulk, and the anomaly is concentrated on the impurity. And then the bulk and the impurity interact.
Yeah. You could have done this in the Ising model as well, couples to some line which is an anomaly.
Well,
even the same model.
Z2 doesn't have anomalies.
Yes,
Z2 is not a good.
Couple the same particle on the circle and put the C. Well, I mean, you would have a U1 on the D.
But the Ising model only has a Z2 symmetry. Z2 doesn't have anomalies. That's why it doesn't work in Ising.
Right. You don't want to consider defects which have more symmetries.
You can, but why would they be preserved under perturbations? You want the symmetries to be.
Just because the defect is guaranteed to be.
Yeah, you can play various games. You can also try to involve time reversal symmetry. Yeah, I don't want to get into it too much now. Okay, so we know that whatever strong coupling, this certainly flows to strong coupling physics. So we know that whatever happens, it cannot be completely screened. It cannot be just a trivial line defect. And now I'm going to use the theorem about the quantum impurity to show you something quite cool. So you can ask, okay, great, we ruled out the unit operator. Can we prove that the halon is not 1 plus 1? Or any number of ones, in fact. Can we rule out this? So we ruled out that. Can we rule out this whole thing? Can we prove that if H is infinitesimal non-zero, of course if H is 0, then the defect is 1 plus 1. It's just a qubit. Can we prove that if H is non-zero, then it cannot be a qubit at long distances. It has to be coupled to the bulk. And here we'll use the theorem about the quantum entropy. So we remember that I told you that if there is any RG flow whatsoever, then S infrared has to be smaller than SUV. We discussed that 2 days ago. SUV here is trivial to compute. In the ultraviolet, H goes to infinitesimal, so SUV is log 2. That's log 2 because there is a qubit in the UV. So because S infrared has to be smaller than log 2, we get an interesting corollary. It cannot be 1 plus 1 because 1 plus 1 at long distances has quantum entropy log 2. And it cannot be 1 plus 1 plus 1 that has entropy log 3. So therefore, we ruled out this whole thing. So using this theorem, we also ruled out that the defect decouples. So if H starts its life as any non-zero number, it cannot flow to a qubit. It has to be coupled to the bulk. The next step is, can we rule out this whole thing? Can we also say that this is non-topological? Yeah.
The rotor really has an infinite number of states. Of course,
Yes.
most of them have a gap. There's no way that coupling to the bulk can somehow close that gap and mess up.
It could be. The gap in the rotor depends on the mass. If you want to be like super clean, and mimic a lattice model, a lattice model would include some antiferromagnet coupled to some qubit in some funny way. So if you want to be super clean, here you would take maybe this limit, so that the gap, you remember that there is a mass in the rotor? Just take it to 0. So the energy levels are n plus phi. Sorry, to infinity, of course, yes. Yeah, you take that, that's it. If you want to be super clean. So you take the mass to be much larger than any other scale, and then it's a very clean problem.
Sorry, RPN?
You just couple the ground states of the qubit, the ground states of the rotor to the bulk.
Kind of remove the Q goes to Q. Really just got a cubic couple of this.
Say again, David?
If you've just got a cubic couple, you don't really have the whole machinery of the anomaly.
Oh, you do, because the anomaly is independent of M. So all you need to do is to take M. This is a dimensionful parameter, because this is dimensionless, and this has dimension 0.5. So H has dimensions of square root of energy. So all you need to do is to take, in fact, M much bigger than some power of H, and that will be good enough.
Maybe I'll say it differently. There's a dimensionless number which is m divided by h squared.
Yes, yes.
Like this. Why can that not flow under Rg and go the opposite way to what we want?
Okay. Let me give you the best possible answer that I can imagine. So technically, M is an irrelevant operator because it counts scaling dimensions. So the action for the qubit is q dot squared plus q dot. Technically, this is an irrelevant operator, while this is a relevant operator. So the first steps of the RG flow are gonna decouple the tower of states and increase this coupling. And it makes a lot of sense to assume that this will continue forever. So it's just like common sense, I would say. How do you know that it's not dangerously irrelevant? I don't know. In the lattice implementations, we don't have a tower of states. We just use the ground states. So we take a limit where M is huge, and we study the system on scales where M didn't have time to. You could also just take M to the huge, and then study the system on energy scales where there is no chance that that tower came down. So it's a question of order of limits. But I believe that the naive intuition that this just decouples in the infrared and this grows is the correct physics. And I'm willing to bet that this is how it works. Because we don't have any indication that the tower comes down from some simple calculation. Okay?
Is it M going to infinity? Aren't the states p squared over M?
Yeah, that's why he confused me.
So M goes to 0?
Yeah, I got confused about I believe that M should be in the denominator, like I wrote at the beginning. That's how you decouple the tower. Because the energy levels are n plus phi divided by 2m. Yeah. So that's why in the beginning I wrote m to 0, but I just cannot figure it out in real time.
I think you're right, because m goes to 0.
Yeah, I think that what I...
Energy is a half mv squared.
Yeah, that's why I wrote at the beginning m to 0, but I just cannot process it in real time. I believe this is the right decoupling limit. That's like the limit that the rotor is very stiff. So I think that's the right one.
The kinetic term goes to 0, basically.
Yeah.
M is in front of the kinetic term.
Yeah. Okay, so now I just want to rule out this option, that it's a topological operator, and that's done by appealing to sociology. There is no mathematical argument for that. Because if it flows to a topological line, it means that there are topological lines in the O2 model. A topological line would be a one-form symmetry, probably non-invertible. And nobody has ever found non-trivial topological line defects in the O2 model in 2+1 dimensions. There is no reason to expect that there are one-form symmetries in the O2 model. So unfortunately, this cannot be ruled out mathematically. I'm just appealing to the fact that we have so much data about the O2 model, and nobody has ever seen a topological line, or had any reason to expect a topological line. So it makes a lot of sense that this can also be ruled out. So therefore, you get an interesting prediction that the halon must be a conformal line operator. And it will be interesting to obtain some predictions about it. There are some simulations already, but there is essentially no theoretical prediction. Yes?
Is this conformal line operator supposed to be stable? Or with this
Completely stable under O2 preserving deformations. So I must say that this is why it occurs so ubiquitously in simulations, because it's completely RG stable. It's completely RG stable if you preserve O2. You can ask, is it RG stable if you break the O2 symmetry? Let's say you break charge conjugation symmetry. Then it's not stable. There are some deformations you can write down. If you break some charge conjugation symmetries, etc., etc. But if you preserve all the O2 symmetries, then I think it's completely RG stable. It's some conformal line operator. We currently don't know almost anything about it. We don't know the quantum entropy. We just know that it's smaller than log 2. We don't know like expectation values in the bulk. How does it influence the bulk, etc. But there is some long story that I don't have time to explain of fractionalization. We know that this leads to fractionalization of charge in the O2 model. I'll just say it just to maybe tease you, but I won't explain what I mean. So in the O2 model, all the charges are integer under SO2. All the local excitations have integer charge under SO2. Here, because of the anomaly, it turns out that some local excitations in the presence of this line defect or this impurity have a half SO2 charge, so they're fractionalized. And it was even recently seen in a simulation that some regions have half particle numbers. So if you measure the particle number in some region, you get a half. So because of the anomaly, some SO2 charges are fractionalized. But I won't go beyond that. I won't explain what I mean precisely. Okay? So that's why some people are also interested in that, because it leads to fractionalization of particle number in the XY model. Yes?
Do you think it's going to be a negative number?
I have no idea.
There is no physical...
No, it's certainly going to be positive. This I can, yeah, actually I can predict that this is true, for sure. The reason I know that is that there is a deformation that breaks charge conjugation symmetry, which leads to a trivial line defect. So there must be an RG flow to a trivial line defect if you break SO2 times C. So therefore it cannot be negative by the S theorem. So it has to be between log 2 and 0. And we know a few other things, but not much. And the last thing that I want to say is a little bit more advanced. So in the last 10 minutes, I'll maybe speed up a little bit. I'll just say something slightly more advanced for people that know about particle-vortex duality. So I just described a conformal line defect, which is O2 invariant in the O2 model. And a famous fact is that the O2 model is a dual to a gauge theory. And I wanted to describe how the duality works. I like that a lot, because it's a very cool demonstration that supersymmetry is still useful. Because I'll explain why now. I'll speed up for the last 10 minutes, because I just want to convey one last point, and that's it. So there is a duality which is called particle vortex duality. which relates the following two models. One is the field theory of a complex scalar field with a quartic interaction. The exact same model that we studied here in 3 dimensions, 2 plus 1. So there is a duality to a gauge theory. So it's a U1 gauge theory plus a scalar field which is charged. Let me choose notation psi. So even though I'm using psi, it's not a fermion. It's a scalar field. So we have a relativistic scalar field with a covariant derivative. And also some quartic interaction. Okay? So there is a fixed point here of the renormalization group. There is a fixed point here. That's just a U1 gauge theory with a scalar field. And they're dual to each other. If you measure the critical exponents, everything agrees. One interesting question is, what is the gauge theory description of the halon? We found the O2 symmetry here. The O2 symmetry here is associated to the current phi star d phi. And also phi going to phi star. That's the discrete symmetry. That's the continuous current. That's a current for the continuous SO2 symmetry. And that's the action of the discrete symmetry C. Similarly, in this model, there is a continuous symmetry with this current. There is a continuous symmetry with this current. That's called the topological conservation law. And there is a discrete symmetry where you take the gauge field to minus itself. That's the charge conjugation. That's SO2. So the symmetries of these models match. They're both O2 invariant. The fixed points match. And we know a lot about this duality. So
sorry, is this also 3D? Or?
Yeah, in 3 dimensions. This is a gauge theory in 3 dimensions. D3x. Now, you can even put this model on the lattice nowadays. It used to be impossible, but now you can put it on the lattice using the Villain formalism. Okay, so this duality can be in principle verified in many, many ways.
Wait, this was put on the lattice in 1978?
Yeah, but it was a lie because they didn't have monopole operators. So when the duality was verified, they couldn't check that monopole operator scaling dimensions agree with the scaling dimensions of powers of phi, because that was an R gauge theory and it did not admit monopoles. Now you can actually put this model on the lattice with a U1 gauge theory and measure monopole operator scaling dimensions for the first time. It wasn't done yet. There's somebody in the audience that's supposed to do it, but doesn't want to. I won't say who, just not to shame the person. And also, well, people know that this is true from superconductivity. That's the effective theory of finite temperature superconductor insulator transition. And we see the XY scaling exponents. So it's been known for decades to be true. So what I want is, what about this? We want to, it's like a dictionary between 2 different descriptions. So I want to pose the question, what is the particle vortex dual of a halon? The halon is an O2 invariant impurity, line defect. What is the dual of the halon? Okay, this is a question that one can pose. If the duality is true, there must be an answer. And I just wanted to give a conjecture for the answer. So, people that work on supersymmetry study something which is a generalization of particle vortex duality. So in the world of supersymmetric quantum field theories, there is a generalization of particle vortex duality, which is called mirror symmetry. And in mirror symmetry, the question of how line defects or impurities map from one side to another has been studied very extensively. And so the inspiration for the answer that I'm going to give came in part from supersymmetry. So I'll just describe a conjecture of the answer, conjecture for the answer. So I guess many of you, I mean, I'm speeding up, so the experts in the audience are tempted to say that it's a Wilson line. Maybe the gauge theory has a very obvious line defect. which is a Wilson line. Right? Is that possibly the answer?
I would think it'd be a monopole. Shouldn't it be a monopole? Because that's the thing that's cool.
Just a second. So is that possible?
C.
Excellent. Who said that? Excellent. So this cannot possibly be the answer because this is not O2 invariant. It does not preserve O2. Shai said monopole. Monopole is not a line operator. It's a local operator.
No, can you construct one using a monopole?
Yeah, but what is the infrared limit? That would be some terrible thing. You wouldn't know what it flows to. I'm going to give a conjecture for the infrared limit. Yeah. So, but it's a good idea. Yes. Yeah. Well, another possible answer is maybe it's a direct sum of a charge 1 Wilson line with a charge -1 Wilson line. Maybe it's some kind of direct sum. Is that possible? No, because that's not possible, because we kind of ruled out. Well, that's not possible for two reasons. One, there is overwhelming evidence that this line operator in the O2 model doesn't exist. There is a lot of strong evidence that this line operator goes to the trivial line at long distances in the O2 model. In the gauge theory, the U1 gauge theory with a scalar field, we have overwhelming evidence that the line operator at long distances is just the trivial unit operator. So the line operator is completely screened. And therefore, this would be just 1 + 1. But I ruled that out by using the theorem about the quantum impurity.
Class, it's not O2 invariant.
And it's not O2 invariant. So, I just wanted to propose maybe a different answer. It can be in principle tested in the future. So an interesting line defect, let's think about the gauge theory in Euclidean signature. A line defect is supposed to be a line, okay? So an interesting line defect is a vortex loop. That's where the inspiration from mirror symmetry came, because they are abundant and they are very, very common in mirror symmetry. So you can define a line defect in the gauge theory by saying that the holonomy of the gauge field is exactly pi. And that turns out to be a charge conjugation invariant constraint on the space of gauge field configurations. Because, well, we integrate over some small circle, S1, of size epsilon. And we impose a boundary. This is a boundary condition for the path integral over gauge fields and psi. So for the path integral. If we impose this boundary condition for the path integral, that the gauge field holonomy is pi, that's a charge conjugation invariant assignment. So this preserves charge conjugation symmetry because the holonomy of the gauge field is defined mod 2 pi. It also preserves SO2. And a somewhat difficult and long computation shows that C times SO2 is exactly minus SO2 times C. So that's a very important consistency check. That this line, the vortex loop has the exact same anomaly as the halon. So it reproduces, so this is anomaly matching. So it also matches the anomalies. Maybe that's the most important consistency check. It preserves the same symmetries and it matches the anomaly. It's not obvious why this defect matches the anomaly, but it is true. So that's a computation that you have to do. You have to try to act carefully on the Hilbert space in the presence of this defect with SO2 and C, and you have to show that on that Hilbert space there is a minus sign. Okay? Yes?
The hard vortex.
Yes, that's exactly why it works.
If I put it on a compact manifold,
This guy's what?
isn't allowed it.
No, it is allowed. Why not?
Further and further away, and it closes back on itself.
It's allowed because it's a gapless system. So you can put a half magnetic monopole somewhere, and the system will just create another half. So if you put it on a sphere, let's say you take a sphere. If you take a compact sphere to be your space, and you put this defect here, it's an impurity at one point, there will be a solution of the equations of motion. There will be just a completely regular solution. The thing is that, as you know, configurations of psi and the gauge field can carry magnetic charge. That's what happens in the ANO vortices. So once you put this boundary condition, it will create a somewhat different profile. But there is a profile which is completely fine. There is no conservation law that says that this is not allowed. There is no Gauss law. If there was a Gauss law and there was a one-form symmetry, then the Hilbert space would be empty. But here there is no one-form symmetry and there is no such Gauss law. So there is a soliton made out of psi and A that cancels that half holonomy. And so what we did in some recent paper with Brandon Rayhound and Fyodor Popov was to calculate the Hilbert space and show that it has a minus sign. That's a concrete calculation. So the way we calculated this minus sign was to solve the classical equations of motion with this boundary condition. And we found two solutions. And then we acted on these two solutions with C and SO2, and we saw that there is a minus sign in the action on these two solutions. It's a classical PDE problem. Okay? And you just see that on these two solutions, charge conjugation is realized projectively. So at the end, you can show this minus sign by some somewhat, it's straightforward, but somewhat technical classical PDE problem.
Just to make sure I understand, you put a constraint, there's a pi flux here around that point, but there is the total flux on the sphere, of course, is multiple of 2 pi.
Yes, that's why, yeah, so the psi and the a's create additional half throughout the sphere.
Right, but are the two solutions related to how this flux is distributed?
Yes, you can act with charge conjugation in one and get the other.
I see.
So the charge conjugation...
Right, so you can go up to 2 pi or down to 0, basically.
Yeah. So, yeah, so as Tim said, so one classical solution basically makes the total magnetic field 0, and the other classical solution makes the total magnetic field 1, and they turn out to be exactly degenerate in energy. And you can also go from one to the other by charge conjugation symmetry, without changing the boundary conditions, of course. That's the most important thing. The boundary condition is charge conjugation invariant, and you map the two solutions to each other. And that's why the SO2 is also realized projectively, because one solution has 0 magnetic flux, the other has 1 magnetic flux. Yeah?
Is this vortex loop not related to constructing a line defect by integrating?
Yes, this should be the infrared limit, but it's extremely difficult to see.
Oh, so conceptually it is that. But
Yes, but how do you see that this is the infrared limit? I don't know. We're saying that integrating a monopole on a line leads to a vortex loop. Okay? So, so anomaly matching works, the symmetries work, and usually, you know, that's a great consistency check. So, okay, so this is the proposal, and there is a very simple way to use the Villain lattice formalism to put this boundary condition. And, well, maybe in the future somebody will check that it's the same as the halon, that it has the same critical exponents. So, so the claim is, I'll just summarize in 5 minutes for questions. So the halon is supposed to be dual to a vortex loop. It matches the symmetries and matches the anomalies. And that's another entry into the dictionary of particle vortex duality. And it's inspired by mirror symmetry, where something very similar happens if you know a little bit about mirror symmetry. So yeah, that's it. Thank you.
Comments, questions, final comments and questions.
I know you said in this case the vortex loop is in the infrared, but more generally, if you have a case where your line defect is from a drilled out hole like this, how do you put on Riemann operators onto the line?
You can integrate operators on the line. You can integrate stuff on the line.
I thought we drilled out. I thought we've lost some space by drilling out.
Yes, so that's a great question actually. So one way to implement it in a simulation, you mean, is to cut out the cylinder and put boundary conditions on the. That's a good, but you have to tell me what exactly to do with psi. And exactly how psi decays. What are the boundary conditions for psi? Maybe psi decays like some power of r, or maybe some other power of r. And these manipulations was what exactly do you do with psi? They are the same as integrating psi on the line. So the two descriptions are the same. You can either integrate psi on the line, or psi dagger psi, for instance. So you could integrate psi dagger psi on the line and ask what does it do, or you could change the boundary conditions of psi near the vortex loop. These are the same things, because yeah, you go between Dirichlet to Robin to Neumann. So yeah. So that's a practical way to try to do that. Yeah.
I hope this question isn't too stupid, but with this gauge theory on the right-hand side, related to David's comment, you can put this on a manifold, and everything could be topologically non-trivial, like U1 bundle could be non-trivial,
Correct.
psi could be non-trivial. And the vortex loop still makes sense in that
Yeah.
thinking, right?
Yeah.
That is, in the duality, is there a not topologically non-trivial version of the left-hand side? Priori seems to make sense.
Well, you see that the map is that non-trivial bundles of the gauge field map to configurations with non-zero charged, non-zero particle number. So on this side of the duality, you can ask.
The field content is the same, I guess, but the fields are the same.
No, the fields are completely different. Here, just a scalar field, complex scalar field, and here there is a gauge field and a scalar field that is charged.
I know, but if you make this topologically non-trivial, what happens to the
Yeah,
fields
so the
here?
other side will have a non-trivial particle number. That's
but still scalar field.
Scalar field, yeah. So the non-trivial bundles map to constant density, to finite density.
I see. So then what would happen to the halon in the...
Well, we claim that the halon is a conformal line defect and goes to the vortex loop. So, okay, somebody one day will just solve the path integral with these insertions and check. I mean, what you can do without doing the explicit computations is like large M, epsilon expansion, and matching anomalies and symmetries. So, yeah, that's all you can do without somebody solving it. Before somebody solves it.
So is Stony charged on any one-form symmetry?
No, there is no one-form symmetry in the system. Also, of course, there is lots of 3D dualities. There is a whole web of dualities in 3 dimensions between Chern-Simons matter theories and other Chern-Simons matter theories, like U1 gauge theory with fermions is dual to something. So there is a bigger question lurking here of figuring out the map between conformal line operators in the 3D web of dualities. And this is just the first instance. You can start from that and maybe derive others.
Question super quickly. Have you already talked about the relationship between anomalies and fusion?
Yes, I did that in lecture 1, yeah.
Okay. Okay. Oh yes, sorry.
Is there at some point that you have fractional charge which is a half? Is this something you easily argued with symmetry, or is it more difficult?
Yeah, I mean, the fractionalization of charge is also clear here, yes.
Okay. So if the duality makes sense, then you
yeah, this duality passes all the simple sanity checks.
Okay.
It matches the symmetries, anomalies, gapped phases, the symmetry fractionalization. You know, all the things that you can check on a piece of paper is okay.
But you're saying that without using the duality, it's harder to understand?
No, the duality is just like a curiosity. It's a new entry into the dictionary.
Okay, so no other question. Let's thank Zohar again for the full set of questions.